Welcome back to the fourth and final video for the gases unit. So we're going to talk a lot about pressure today. And we're going to start with Dalton's law of partial pressures, which is a very simple gas law at this level. And basically, it says that a mixture of gases, its pressure is equal to the sum of all the gases added up. So the picture is worth 1,000 words, and it makes you understand how simple it is. Here's a sample of oxygen with a pressure of 2 atmospheres, and a separate container of nitrogen with 3 atmospheres of pressure. If we mixed these two things together, the new pressure is just the sum of the old. And we would do this for as many gases were added to a mixture. All right, pressure total is 1 plus 2 plus 3. That's it. That is, for New York State's Regents Curriculum, that's what Dalton's law of partial pressure talks about. So we'll just look at these two examples. Okay? If there is a mixture of hydrogen and oxygen in a container, if that container has a total of 10 atmospheres, and then we have a partial pressure of 7 atmospheres coming specifically from the hydrogen, what is the pressure exerted by the oxygen? Well, if the mixture is 10 and the oxygen, and the oxygen is 7, then the mixture is a sum of the, I'm goofing all over the place here. This is not the oxygen. We're looking for the oxygen. What we have is the hydrogen. What we're looking for is the oxygen. And you would just solve for it. 7 plus whatever the oxygen was is the total of 10. And that would lead us to 3. Okay? That's it. That's Dalton's law of partial pressure. Now, vapor pressure is something a little bit different. Now, on our reference table, this is going to be table H, is where we should be looking. Okay, so if you have time, you should take out your reference table, go to table H, or just pause the video, come back to it as soon as you find it. But this is what table H looks like. All right, what it shows is vapor pressure along the y-axis and temperature on the bottom. Now, there are a couple ways to read this. I like to just kind of think of the boiling point situation. So we'll talk about that in a minute. But vapor pressure is the pressure exerted by a gas on its surface. Essentially, this is what keeps a liquid a liquid. If you have a beaker filled with a liquid, it's a liquid because it doesn't have enough kinetic energy to be a gas. Its intermolecular forces keep the molecules close together, yes, but it's also a liquid because there is a force pushing down on the surface of the liquid. So all three of these things kind of help determine the phase of a molecule. Well, if that pressure starts to be removed, and we're not changing the temperature, what starts to happen is liquid can turn into gas. And we could start to get some boiling happening at different pressures, therefore at different temperatures. So basically, when we change the vapor pressure, we're changing the boiling point of a liquid. We can get water to boil at a temperature other than 100 degrees Celsius. For normal boiling points, we stick to standard pressure. 1 atmosphere, 101.3 kPas. Those will tell us the normal boiling points of a substance. For instance, 1 atmosphere or 101.3 kPas, water has a boiling point of 100 degrees Celsius. I could use the table that's given to us to prove that. Here is our standard pressure value. It's even highlighted for us on this table. And if I took this line, which tells me what normal pressure is, and I bring it over to water, what do I find? I find that the boiling point of water is 100 degrees Celsius. So the temperatures I like to look at as the new boiling point at various vapor pressures. So, if we were to climb up to Mount Everest, where the pressure or the atmospheric pressure is much lower, we would have a lower pressure pushing on top of a liquid. Let's just say it's half. It's not, but let's just say it's half. Well, at the top of Mount Everest, where there's half the pressure, water has a much different boiling point. Water is now looking like it's boiling at about 83 degrees Celsius. Essentially, the molecules don't need the same amount of energy to break apart because there's not the same amount of force pushing down on their surface. And so that's exactly what this chart tries to show. The change of vapor pressure and how it influences and changes the temperature of a liquid. One more thing I want to mention for you on this chart specifically is propanone can be identified as having the weakest intermolecular force. And the reason it can be identified as having the weakest intermolecular force is because no matter what the pressure is for propanone, no matter what the pressure is, keep an eye on the red, right? It will always be, get you a good color here, we'll use green, it will always be the lowest boiling point on the table. Right? You could look at the red, you could look at the green. Right? But propanone, regardless of which things we're talking about, is always going to have the lowest boiling point at any given vapor pressure. And the relationship from intermolecular forces was the weaker the intermolecular force, the lower the boiling point. So with that said, as we go further and further, weakest intermolecular force, stronger intermolecular force, ethanoic acid is going to have the strongest intermolecular force. So, in truth, for this chart and the regions, you really just need to be able to read it. And you need to be able to determine that the only thing that's really not written here is the intermolecular forces. But if you know your rules of them, it's pretty easy to figure out. So that's how we're going to read Table H. And that concludes the gases unit for New York State Regents. I hope that you have learned. I hope that you feel a little bit more confident in how gases behave and how we're supposed to attack this Regents curriculum. And I hope you please like the video, subscribe for more content, and we'll catch you in the next unit, which is going to be solutions. Thank you.